In a delta system, the neutral is typically established by the transformer's internal connections. Often, this neutral is not brought out as a conductor. While sometimes a fourth wire is present, it's uncommon, and it should never be grounded directly. Ground faults on a delta system will clear through several mechanisms. Firstly, an overcurrent protection device, or OCPT, will trip if the fault current is sufficiently high. Secondly, the conductor itself might melt due to the excessive fault current. Thirdly, the primary protection device on the transformer, such as a fuse or a recloser, could trip to isolate the fault. A situation was observed where a three-phase riser had a fourth wire extending from the weatherhead, yet it was coiled up and not connected. Given the presence of a single-phase service utilizing the neutral, it is recommended to contact the utility to have this fourth wire connected to the system neutral. When measuring voltage between phase and ground in a grounded neutral system, the neutral should read slightly less than half of the phase voltage. If the measurements are closer to half of the phase-to-phase voltage, it could indicate that the transformer neutral is not properly connected. In such cases, the measured voltage might be from an induced neutral, which would be proportional to the phase-to-phase voltage. Consider a scenario where you have a three-phase delta system feeding a commercial building. If a ground fault occurs on one of the phases, a large current will flow from the faulted phase to ground. The path this current takes depends on whether the system is grounded or ungrounded. In a grounded delta system, a grounding transformer is used to create a neutral point. This neutral point is then connected to ground. When a ground fault occurs, the fault current returns to the source through the grounding transformer and the grounded neutral. This high current will trip the overcurrent protection device, such as a circuit breaker or fuse, on the faulted phase, thus clearing the fault. In an ungrounded delta system, there is no direct connection to ground. When a ground fault occurs, the fault current is limited by the capacitance of the system to ground. This capacitance is due to the inherent capacitance of the conductors, equipment, and other components in the system. The fault current in an ungrounded system is typically much lower than in a grounded system. This lower current may not be sufficient to trip the overcurrent protection device. However, the presence of a ground fault in an ungrounded system will raise the voltage on the unfaulted phases. This increased voltage can stress the insulation of the equipment and conductors, potentially leading to additional faults. For example, if the system voltage is 240 volts, and a ground fault occurs on one phase, the voltage on the other two phases will rise to approximately 208 volts to ground. This is because the line-to-line voltage remains at 240 volts, but the reference point has shifted due to the ground fault. Ground faults in ungrounded delta systems can be difficult to locate because the fault current is low. Specialized ground fault locators are often used to trace the fault current and identify the location of the fault. These locators typically use a high-frequency signal to inject a current into the system and then measure the current flowing through the ground conductors. In some cases, a delta system may be corner-grounded. In a corner-grounded delta system, one of the phase conductors is directly connected to ground. This type of system is relatively rare, but it can be found in some older installations. When a ground fault occurs on a corner-grounded delta system, the fault current is very high, and the overcurrent protection device will trip quickly. Corner-grounded delta systems are generally considered to be less safe than grounded delta systems because of the high fault currents. When troubleshooting a three-phase delta system, it is important to first determine whether the system is grounded or ungrounded. This can be done by measuring the voltage between each phase and ground. If the voltage between each phase and ground is approximately equal to half of the phase-to-phase voltage, then the system is likely grounded. If the voltage between each phase and ground is not equal, then the system is likely ungrounded. It is also important to check for the presence of a grounding transformer. A grounding transformer is a special type of transformer that is used to create a neutral point in a delta system. If a grounding transformer is present, then the system is likely grounded. Understanding the different types of delta systems and how ground faults are cleared is essential for ensuring the safety and reliability of electrical installations. Consider the various scenarios and protective measures to maintain a safe environment. When encountering a situation like the one described, it is crucial to verify the grounding configuration of both the single-phase and three-phase services. Disconnecting the power and performing thorough continuity tests between the neutral, ground, and each phase conductor can help determine if the grounding is properly implemented. Furthermore, inspecting the transformer connections and the utilities grounding practices is essential to confirm that the system is operating as intended. If the measurements indicate an ungrounded system when a grounded system is expected, immediately contact the utility company. Operating an ungrounded system when it should be grounded can lead to significant safety hazards and equipment damage. The utility company can investigate the transformer connections and ensure that the neutral is properly grounded, if required. In addition, consider the impact of unbalanced loads on the system. Unbalanced loads can cause voltage imbalances and circulating currents in the neutral conductor, which can exacerbate ground fault conditions. Analyzing the load distribution and implementing measures to balance the load can help improve the overall system performance and reduce the risk of ground faults. Also, ensure that all equipment is properly grounded according to the National Electrical Code, or NEC. Proper grounding provides a low impedance path for fault currents to return to the source, which helps to trip overcurrent protection devices quickly. Pay particular attention to the grounding of motors, transformers, and other large pieces of equipment. Consult NEC Table 250.122 for proper equipment grounding conductor sizing. If there is any doubt about the safety or integrity of the electrical system, it is always best to consult with a qualified electrical engineer. An electrical engineer can perform a thorough system analysis and recommend appropriate corrective actions. Neglecting potential grounding issues can lead to severe consequences, including electrical shock, fire, and equipment damage. It is critical to prioritize safety and ensure that the electrical system is properly designed, installed, and maintained. It is also important to regularly inspect the electrical system for any signs of damage or deterioration. Look for things like corroded connections, damaged insulation, and loose wiring. Any problems should be addressed promptly to prevent them from escalating into more serious issues. Additionally, consider the use of ground fault protection devices. Ground fault protection devices are designed to detect small ground faults that may not be sufficient to trip standard overcurrent protection devices. These devices can help to prevent electrical shocks and fires. There are several types of ground fault protection devices available, including ground fault circuit interrupters, or GFCIs, and ground fault equipment protection, or GFEP. Also, document all findings and actions taken during the troubleshooting process. This documentation can be helpful for future reference and can also be used to demonstrate compliance with safety regulations. Maintaining accurate records of the electrical system can help to ensure its long-term reliability and safety. It's essential to understand the different types of overcurrent protection devices and their characteristics. Fuses, for example, are single-use devices that must be replaced after they trip. Circuit breakers, on the other hand, can be reset and reused. However, circuit breakers can degrade over time and may not trip as quickly as they should. Regular testing of circuit breakers is recommended to ensure that they are functioning properly. The NEC provides guidance on the selection and installation of overcurrent protection devices. It is important to follow the NEC requirements to ensure that the electrical system is properly protected. Furthermore, consider the impact of harmonics on the electrical system. Harmonics are currents and voltages that are at frequencies that are multiples of the fundamental frequency. Harmonics can be generated by nonlinear loads such as electronic devices and variable frequency drives, or VFDs. Harmonics can cause a number of problems, including overheating of equipment, voltage distortion, and interference with communication systems. It is also important to understand the different types of wiring methods and their applications. The NEC specifies the allowable wiring methods for different types of occupancies and environments. It is essential to follow the NEC requirements to ensure that the wiring is properly installed and protected. Regularly inspect the wiring for any signs of damage or deterioration. Look for things like cracked or brittle insulation, loose connections, and corroded conductors. Any problem should be addressed promptly to prevent them from escalating into more serious issues. Additionally, consider the use of surge protection devices. Surge protection devices are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes or switching operations. Surge protection devices can help to prevent damage to sensitive electronic equipment, such as computers, televisions, and appliances. There are several types of surge protection devices available, including whole-house surge protectors and point-of-use surge protectors. It is also important to understand the different types of transformers and their applications. Transformers are used to step up or step down voltage levels. There are several types of transformers available, including dry-type transformers, oil-filled transformers, and auto-transformers. The selection of the appropriate transformer depends on the application and the voltage levels required. When working with electrical systems, it is essential to follow all safety precautions. Always to energize the circuit before working on it. Use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Be aware of the potential hazards of electricity and take steps to mitigate them. In addition, ensure that all electrical work is performed by qualified personnel. Only licensed electricians should perform electrical work. Attempting to perform electrical work without the proper training and experience can be dangerous and can lead to serious injury or death. Consider the benefits of using energy-efficient equipment. Energy-efficient equipment can save money on electricity bills and can also reduce the environmental impact of the electrical system. There are many types of energy-efficient equipment available, including LED lighting, high-efficiency motors, and energy-efficient appliances. Additionally, conduct a regular electrical safety audit. An electrical safety audit can help to identify potential hazards and can also help to ensure compliance with safety regulations. A qualified electrical inspector can perform an electrical safety audit. By following these recommendations, you can help to ensure the safety and reliability of the electrical system. Prioritize safety and seek professional assistance when needed. Consistent monitoring, inspection, and maintenance are key to preventing electrical issues and ensuring the long-term performance of the system. It is also important to consider the specific requirements of the occupancy. For example, a hospital will have different electrical requirements than an office building. The NEC provides guidance on the electrical requirements for different types of occupancies. It is essential to follow the NEC requirements to ensure that the electrical system is properly designed and installed for the specific occupancy. Additionally, familiarize yourself with the local electrical codes and regulations. Local electrical codes and regulations may be more stringent than the NEC requirements. It is important to comply with all applicable electrical codes and regulations. Regularly review and update the electrical system documentation. The electrical system documentation should include drawings, specifications, and maintenance records. Keeping the electrical system documentation up to date can help with troubleshooting and maintenance. Also, consider the use of a power quality meter. A power quality meter can be used to measure voltage, current, frequency, and other electrical parameters. Monitoring power quality can help to identify potential problems with the electrical system. In addition to the NEC, there are other standards and guidelines that can be helpful for designing, installing, and maintaining electrical systems. These standards and guidelines include those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to be familiar with these standards and guidelines and to follow them when appropriate. The specific scenario described involving the unattached fourth wire and the three-phase riser is especially critical. Since a single-phase service is already using the neutral, there is a clear indication that the utility intended for the three-phase service to also have a neutral connection. Not connecting this neutral can lead to unbalanced voltages and potential safety hazards. Contacting the utility to connect this neutral is not just a good idea, but a necessary step to ensure the safe and proper operation of the electrical system. It is also a good practice to verify that the utility has properly sized the neutral conductor to handle the expected load from both the single-phase and three-phase services. An undersized neutral conductor can lead to overheating and potential fire hazards. This situation highlights the importance of communication and coordination between the electrician and the utility company. Open communication can help to prevent potential problems and ensure that the electrical system is properly installed and maintained. Remember, the electrical system is a complex and interconnected system. A problem in one part of the system can affect other parts of the system. It is essential to take a holistic approach to troubleshooting and maintenance. By understanding the principles of electricity and following proper safety procedures, you can help to ensure the safe and reliable operation of the electrical system. The observation of 120 volts on two legs and 208 volts on the stinger to ground in the three-phase service further emphasizes the irregularity. This voltage pattern is not consistent with a typical grounded delta or Y system, indicating a potential issue with the transformer's grounding or internal connections. The induced neutral theory suggests that the absence of a direct neutral connection causes the system to rely on capacitive coupling to ground, resulting in the observed voltage readings. This situation is not ideal, as it can lead to unpredictable voltage fluctuations and increased risk of equipment damage. To summarize, always prioritize safety, ensure proper grounding, and seek professional help when needed. Continuous learning and attention to detail are crucial for ensuring the safe and reliable operation of electrical systems.